Welcome back. Yes, there is an app that we can use online as well. Which one have you got? For an E6B?
I have free E6B.
Yep, is that the Sparky one? Yeah, I've got the same thing, I think.
I don't know, it says free E6B.
Yeah, there's a couple of them out there, and yes, they do work. The ones that are online are fine. These are fine too, except they won't let you take that into the exam, right? It's an iPad. No, it's not so much that. It's just the fact that if you can connect to the internet, it's not going into the exam. They won't let you take it in. So you can take one of these. You can take an electronic flight computer in. That works as well. You're going to have to prove that the memory has been erased, that there's nothing in memory. You can take a calculator. You have to show there's nothing on the memory. You cannot take a phone, an iPad, any smart device to get in because you can connect up. And they'll have a TV camera in there watching you because it's a proctored exam.
Smart devices like smartwatches?
Yeah, I can't answer about the smartwatch. That's a good question. I don't know what the answer is on a smartwatch. That's a really good question. Yeah, what I would ask, I would call the 800 number and double check before you wear it into the place. All right, so using the E6B on the written exam, and a couple of things to remember, it's actually a very simple device to use. And as I mentioned earlier, the E6B has been around since World War II. It's also called the Dalton flight computer because the guy that invented it was a guy named Dalton. It's a circular slide rule. But the thing you got that's going really well for you that did not work for me in 1975 was in 1975, the directions that are printed on the face of it and on the wind side on the back had to be taped over with white tape. I wasn't allowed to have the directions in 1975. You are. So if all else fails and you completely forget how this device works, read the instructions. They are there. You cannot take the booklet that came with these, but you can take whatever's on the face of it already. So there's a few things to understand about how the E6B works. They start with the scales. We're dealing with an inner scale that rotates when we turn the bezel. That's this portion, and an outer scale. And the outer scale can represent different factors. They move, the inner two scales that move are always representing time. And you will see on the two layers of that inner scale, one of them labeled minutes and seconds, and the inner one labeled hours. So this is always units of time. The outside are things that happen in a 60-minute period of time, such as miles traveled or gallons of fuel consumed. So what we need to watch out for is what those scales represent. The markings between the numbers vary depending on where they're positioned around the outer portion of the scale. For example, if I look at the number 15 and the number 16, I'll notice there are 1, 2, 3, 4, 5 markings, 5 hash lines between this and 16. But if I look between 14 and 15, there's double the number. The number of lines on that scale between 1,4 and 1,5, there's actually 10 markings there rather than 5 there. See how it changes depending on where you are on the outside scale? It is just about an issue of interpretation, and you need to count those marks depending upon what value you're trying to read to be sure that you are reading the scale correctly. The instructions are important. The primary use for this side of the flight computer for the private pilot written exam is going to be calculations of time and distance and calculations of fuel burn. Time is usually calculated in terms of nautical miles and knots. In fact, on the written exam, those are the only scales they do. They will not use statute miles, and they will not use miles per hour. So all of the questions that you're going to have to calculate are going to be based on nautical miles and knots per hour. How many nautical miles per hour am I traveling? And the directions are going to be here. To compute solutions for time, rate, distance, or fuel, I have a black arrow that is at the 60 point on the inner scale. You all see that? That black arrow points to how many things happen in 60 minutes. And I will look on the outer scale, in this case a time distance calculation, miles per hour. The scale is pointing, the arrow pointing to how many knots I am traveling in speed. The distance is on the outer scale, and as I said earlier, time is always on an inner scale. So, here's an example. Given that I have a ground speed of 80 knots, and I am traveling a distance of 59 nautical miles, what is the time to go en route from point A to point B given these two factors? Go back to the direction for a minute. If my speed is 80 knots, I want the black arrow to be pointed to a number on the outside ring that represents 80. You've got it. How are you doing? Perfect. You guys in the same point? 80. Perfect. Yep. We're all there. You okay? Yep. How are you? Perfect. Great. All right. So we've set the problem up. That's the only movement we've got to make. The next point is, if I've got the arrow pointing to 80 knots, the question I've got to answer at this point, and I left my clicker over there, is I am traveling 59 nautical miles, correct? Is that going to take me more than an hour or less than an hour? Less. I'm traveling at 80 knots, 80 nautical miles in 1 hour, and I'm only going to go about 60, 59 of those. So I'm going to look on the outer scale for something that represents 59. Underneath that is going to be my time. Is that what you come up with? Which one of those answers is closest? Yeah. You will get close enough to find the answer. Now, that is a small airplane. I mean, let's face it, an airplane flying 80 knots, even a Warrior is going to get me someplace at over 80 knots. Let's try the same problem. But instead of doing 80 knots, let's look at an airplane that's doing 160 knots. Same distance, 59 nautical miles. Now I'm flying a higher performance airplane. It's going 160 knots, and I'm doing it at 59 nautical miles. Nope. Point the arrow to 160 instead of 80.
This thing to 160?
160.
Okay.
Okay. Now 59 on the outer scale. What do you get? Yep, that's now our speed. 160, not 60. 160, double the speed. Okay. Right, 160. All right, 59 on the outer scale. What's my time?
22.
Yep.
22.
Does that make sense? If we double the speed of the airplane, the time to go 59 miles just went from 44 minutes to 22 minutes. Okay, that 1.6 is pretty good because that 1.6 could represent 16. It could represent 160. But let me put the problem to you another way. Let's say I'm flying a fighter of some type, and that's now 1,600 knots. I'm breaking the sound barrier. I'm probably going Mach 2 at that point. 1,600 knots. How long is it going to take me to travel 59 minutes without moving it, because you've already got it pointed to 16?
2,400.
22 what? 22 or 2.2? 2.2 minutes? How many minutes is it going to take me to travel 59 nautical miles at 1,600 knots? Yeah, the number is the same. Do you see what I'm getting at here is the value could be 20, could be 2.2, it could be 22, it could be even longer. It's all about where do I put the decimal point, but the value is the same. That side of the computer will work time distance problems, whether I'm flying an F-16, a J3 Cub, or anything in between. The flight computer does the same calculation. It doesn't matter. Let's try a different one. 44 minutes was correct for that problem. Agree? All right, now let's try another one. Ground speed has gone up to 103 knots. So I have to reposition the arrow to 103, and my distance is 58 nautical miles. The question again is time. So where's 58? So how much time is that going to take me of those answers?
B, 34.
Does anybody agree? No? You disagree? What do you got, Richard?
A, 27.
27. Ooh. What's the answer, gang? 103 knots and a distance of 58 nautical miles takes us to 34 or A? Now you can do this on a calculator. Like I said, you're allowed to take a calculator into it. Same thing, 58 divided by 103, 0.56. 0.56 times 60 minutes in an hour gives me the same answer. So you have options on how you want to calculate this. But this is a very simple matter. All I got to do is point the black arrow at 103 knots, and I'm going to come up with, but I got to interpret properly. I have to look at the scales to be sure I'm reading it properly. Okay? All right, so what is your time en route to your destination? Your ground speed is 80 knots. The distance is 54 nautical miles. We're going back to an 80 knot question. Black arrow points at the 60, arrow points at 80. That's how fast I'm traveling. And my distance is 54 nautical miles. 4 nautical miles. 40 what? 40. The closest answer should be pretty straightforward. It's going to be here. Notice that, look, immediately I can throw one of these out. Can I not? If I'm traveling 80 and I'm traveling 80 knots and I'm traveling less than 80 knots, it can't be more than an hour. So right off the get-go, I can throw out question answer C. That is not even in the realm of possibilities. But these two are only 5 minutes apart. It's going to be pretty easy, if you're not careful about how you're reading it, to pull up the wrong answer. Two answers are close. In this case, our answer is 40 minutes. That's the best answer. All right, ground speed, faster airplane. We're back to a fast aircraft. 174 knots is our ground speed. Our time, we're flying for 40 minutes. We're going less than 174 miles, but the distance traveled in nautical miles. .174, I want to see that you've got it set right. This is the catcher. Now we're looking at minutes on the inner scale. We don't know the distance. They're telling us we're flying at 174 knots for 40 minutes. What is that in distance? 116? Are you okay with that? Look again at how close A and B are. So 116 is our answer. So there's the problem setup. As you see, the 60 is pointed at 174, 170. The hash marks between the 170 and the 180 are in increments of 2. So at this point, I'm looking at 170, 172, 174, 176, 178, 180. 174 knots is pointed at this point. Time is 40 minutes, and it's right across from 110, 115, 116. That's my answer. Time is always the inner scale. Simple answer.
So on that example, if you go back, right by between the 70 and the 80 on the inner scale, it says minutes,
Yes.
and then hours on the other side.
Correct. Hours down here, minutes here. So in this case, 40 minutes. This could be 400 minutes. Remember, depending on how we're, which could be over 6 hours. But in this case, we're only dealing with 40 minutes, so the hours aren't going to apply.
So on mine, it says on that inner scale seconds. Is there a different reason why that would be?
Oh, you've got seconds. Yeah, it could be seconds. Again, if this were, instead of 174, what if it were 1740? Then it would be seconds. It depends on what this value is. This value is 100.
Yours says minutes right there. Mine says seconds.
Yeah, it could be. It doesn't matter. It's time. The issue here is that it's time. Yep. Yep. It will. Statute. Time. Seconds and calibrated airspeed, and it's just meant to be time. It could be seconds, it could be minutes, it could be hours. It doesn't matter. This could be either one.
It says hours, yeah.
Yeah, it does, but this could be either one. The black arrow always represents how many things happen in a unit of 60, in 60 minutes or 60 hours, 60 seconds. But in this case, we're dealing with how many things happen in 1 hour. In this case, we are traveling 174 nautical miles per hour. 116 is our answer. Now, the other thing we do with the flight computer is our wind correction angle. So we know that if it were possible that I needed to fly from this point in space to that doorknob in the center door of the back of the room, if I point the airplane at it and I just fly straight for it, in a zero wind situation, everything's going to work fine. But the fact of the matter is, there's always a wind from someplace. And if I don't compensate for that wind, I'm not going to get directly where I want to go. For sake of argument, let's say the wind's coming in through the windows behind this curtain, and it's blowing straight across the room that way. If I launch myself to that door, and I don't compensate for the wind, I'm going to end up going over here someplace. Make sense? Because the wind is going to be blowing me off course. So I need to adjust. I've got to turn into the wind to some extent to compensate so that my track over the ground is going to take me to that point in space. How do I calculate that? There's two ways to do it. There's what we call a wind triangle, which, by the way, has just been added back into the written exam. Yes, they weren't even there in 1975 when I took the exam. It was gone by then, so they've put it back in. The other way is the wind correction side of the flight computer, which is the back side of it. And for this, you're going to need a pen or a pencil. Now, this is a really simple system to operate, but the easiest thing to do is to remember to read the instructions that are at the top of the sliding card. So David, read me slide instruction number 1 on the top of the card on the wind side. Flip it over.
You might only have it on the wind side.
Oh, you've got it on the, oh yeah, you do have it on the
Flip
wind.
it over. Just flip the card over.
Yeah, flip the
Pull
card
it
over.
out, flip it over.
There you go. Great. Now, read me step 1.
Place wind direction under true index.
All right, it says place wind direction under true index. There is an arrow at the top of the circle in the card. It says true index. The reason it's asking for true index is that when we are calculating wind corrections, we are generally using a number that comes from what is called the winds aloft forecast. And those winds are given relative to true north, not magnetic north. We steer a course based on magnetic compasses. But the winds information that we are given for calculation on a cross country are given to us relative to true north. So we start by putting the wind direction under the true index. So number one, here's a course. True course is 165. The wind is coming out of 180 degrees at 28 knots. True airspeed of this airplane is 140 knots. Step one, wind direction under true index. Wind direction, 180. So we turn the wheel until the letter S is under the arrow and then stop. Now, what's step two? James, read me the second instruction.
It says mark W wind dot up from G the grommet.
Okay, the grommet is the center hole in the middle of that plastic circle. Y'all got one. Some of them are plain, some of them have a metal grommet stapled in there. It doesn't matter. Either way works. It says mark wind velocity up from the grommet. What I tend to teach students is slide the card so that the grommet is sitting at a number. You'll see each of those arches underneath there. Each of those arcs is measured with a number. Run it down till you got the grommet over the 100 knot line. It's easier to count from there. Our wind speed's what? 28 knots, correct? So I'm going to count up from that 100 and put an X, just like you see on the slide, at 28 knots. Now they counted up from 200. I don't care. It doesn't matter. Whatever's easy for you to count up 28 knots and put an X so that the cross of the X is on the center line of that circle. And you can erase this with a little bit of spit on the end of your thumb. So don't panic. These aren't permanent. Just don't use a Sharpie to do this, because that's going to be harder to get off. Step three, place the true course under the true index. We're now going to rotate the card again. Or rotate the circle, not the card. Circle says, place true course under true index. The true course is 165 degrees. So I want to now rotate this thing to 165 under the true index. Great. You got it? 165, 165, you're good. Quick, not bad. You're there, you're there. All right, now, step four is slide the true airspeed under the wind dot. What's the true airspeed given to us in this? 140. The true airspeed line is the mark you just put on it. That is your true airspeed. I'm going to take the card and slide the card now so that the little X I just put on the circle on this thing lines up under the 140 knot line. So slide this up, the 140 is there. Perfect. You're done, folks. You've got it set. What have I got? Well, that little mark that you put on there, when you slide it to 140, you're going too far up, aren't you? Yeah. Great. All right, the ground speed is now read under the grommet. What this is telling me is I've got a bit of a headwind here. So if my true airspeed is 140, what's my ground speed going to be given these winds? 113? Agree? Close enough? 113? It's slowing me down, is it not? And I have to compensate by turning the aircraft to the left or the right. I have to turn to the right. How many degrees? 3. Those little lines are going to show you how far you have to turn the airplane. There's 5 degrees, 3 degrees. So it's not much of a wind correction angle. It's a very shallow 3 degrees to the right. And it's going to slow me down. But under these conditions, winds coming out of the south at 28 knots, and I'm flying 165, which is southeast, I've got to compensate with a 3 degree turn to the right. It's going to slow me down to a ground speed of 100 and whatever, 13, 16, and I have a 3 degree correction to compensate for the wind. There's my answer. Now, 3 degrees to the right. If my true course is 165 degrees, 3 degrees to the right, do I add that 3 degrees or do I subtract that 3 degrees? If I look on this thing someplace, it's going to tell me that if I subtract it if it's to the left, and I add it if it's to the right. There is a little mark at the bottom of it. Well, they're in different places. There, yours is on the card. Exactly. Where's yours, Mitten? Yep. Perfect. If it's to the right, I have to add it. So my true course, 165, if I add 3 degrees to it, my true heading now, 168. So what I've now got, here's where I'm going. I had a true course. My true course was 165 degrees. I established a wind correction angle. The wind correction angle was 3 degrees to the right. We've already established that if it's going to the right, I have to add it. The result of this is a heading. Remember, the direction the airplane is pointed to compensate for wind, 165 plus 3 takes me to 168 degrees. So that's the heading. The problem is this is relative to true north, and I fly based on a magnetic compass. So I have to convert that number, my heading, into a magnetic heading. And I can also have a magnetic course. The difference to go from here to here is plus or minus the magnetic variation, which is the difference between true north and magnetic north, which varies tremendously depending on where you are located. Interestingly, here in Florida, the 0-degree agonic line, the line where there is no difference between true and magnetic, is just off the west coast of Florida as you head toward Louisiana. So where we are located in central Florida, we have a magnetic variation at this point in the state, somewhere about 5 or 6 degrees to the west. And so we will have to add or subtract variation. We're going to get into that. We haven't gotten there yet. All we're doing at this point is wind correction angle. We're using this side of the computer to enable us to figure out what is the effect on our ground speed by having a headwind, and how much of a correction factor do I have to put in to compensate for that wind. So slide the true airspeed under the wind dot, take it to 140. I read the ground speed under the grommet, 110, 111, 112, about 113 is the ground speed. And the wind correction angle under the wind dot you just made from here to here, there's 5 degrees, there's 10 degrees. It comes out about 3 degrees to the right. And so my true course plus the correction to the right, or minus if it was left correction, I subtract it. So 165 plus 3 degrees takes me to a true heading of 168. Then I have to compensate for magnetic variation to get the magnetic variation. The magnetic variation is shown on the sectional chart. So let's take a look at that for a minute. This is Florida, this is Orlando. Let's take a look at where this would look at. Let's go. Okay, see this line, the dashed magenta line? This is telling me that at this point in the state, the magnetic variation is 5 degrees to the west. If I go the other direction, yeah, you can barely see it because of the clutter on Orlando, but there is the 6-degree west line. And as we keep going out east, that variation continues to be westerly variation. Now you notice on your computers, going back here to this example, it tells me my true heading, 168. The variation in this example from this sectional chart is 3 degrees west. It all depends on where you're flying. The sectional charts will tell you. Each line change is 1 degree, and as you get closer to the 0 agonic line, they actually go in half-degree increments. So you pick the closest agonic line to the center of your cross country, and you use that as your justification. Look, your compass is graduated in 5-degree increments. The directional gyro in your airplane is graduated in 5-degree increments. Your flight check is based on being able to hold a heading plus or minus 10 degrees. Nobody's going to expect you to fly plus or minus 1 degree. Even airline transport pilots aren't required to do that. ATP check ride is plus or minus 5 degrees. So let's keep this in perspective. Being off by 1 degree isn't going to make a big difference in the real world. So in this case, my true course was 165. The wind correction angle was plus or minus, was in this case plus 3 degrees, gives me a true heading of 168. The variation off of the chart was 3 degrees to the west. The way the variation correction works is this. East is least, west is best. That's the mnemonic to tell whether I add or subtract it. If the variation is easterly, I subtract it. If it's westerly, I add it. In my case, 3 degree west, so I'm going to add that variation to my true heading. The magnetic heading is now 171 degrees. In this case, we were talking 3 degrees west. Gives me a magnetic heading of 171 degrees. Normally, all I would do is find that on my compass and fly it. But the FAA understands that every compass has an error. And that error is corrected, that underneath each of your magnetic compasses is what's called a compass deviation card. And in this case, what happens is the manufacturer of the compass is going to check it, calibrate it with the airplane with all the engine running and all electrical systems on, because it creates magnetic fields in the aircraft, and it will cause a slight error in the compass. Is it significant? Well, take a look. In this case, for a heading of north, I need to steer 0. So the north is right dead on. But if I look at for south, it's going to be off by 1 degree. Remember what I said? It's very difficult, if not impossible, to steer plus or minus 1 degree. But if I look at heading of west, which is 270, it's off by 4 degrees. So the worst deviation, what I need to do here is figure out what is my compass deviation. So my magnetic heading is 171 degrees. I've got 150, I got 180, and I got 210. This is the closest thing I can get to 170, and it is 1 degree off. So the compass deviation is off by 1 degree. This is what we call the course heading, or that's what I'm going to steer on my compass to get from point A to point B. You need to be able to do that for the written exam. The real life reality check is plus or minus 1 degree, you can't fly anyway. But on the written exam, when they give you a cross-country question to answer, they're going to give you that deviation card. That deviation card is figure 58 in your test supplement book. Steal yours for a minute. Figure 58. It's right there. Okay? So when they give you something to calculate, and they tell you to include the deviation, you better include the deviation, because if you don't, there's going to be 2 answers that are going to look really, really good. And if you don't look at this, you're going to get the wrong one of them. See my point? You got to use all of the available information. So true course, correct for the winds, gives me a true heading, because my winds are based on true north. But I fly by magnetic compass. I adjust for the variation. I end up with a magnetic heading. I adjust that magnetic heading with the deviation card given here, and it gives me my final course heading of 172. And it will get me from point A to point B. Now, how big a deal is this? Let's put it in perspective. If you are 1 degree off course and you fly for 60 nautical miles, you will be 1 mile off course. That's not a lot. You're still going to find it. The way I was taught, and what I try to be sure all students understand, is that flying is a series of small corrections. We need to be looking outside the window. The problem we have in this day and age is with a GPS, I become a child of the magenta. I follow that purple line. Well, the problem is that purple line, there can be other issues that come up. We still need to be able to know how to plot a course, how to do a wind correction angle, and how to check my course along the route to be sure I am where I need to be. Trust me, if you do these small corrections and check along your route, you will never be a mile off course. You will be within tighter tolerances. It's not that hard. We don't want to become, we love the technology, don't get me wrong. I love glass cockpit technology. I love GPSs. They enable us to do some fantastic stuff. But you never need to become dependent. You need to be able to do these calculations, because guess what? FAA is going to make you do those calculations. And you'll still have to do them on the instrument written. There's still cross countries that have to be planned. And still the same way, except you're using low in route charts rather than sectional charts. So these are things you're going to have to do again.